Hey guys, welcome to Unit 14 Notes A. Today we're going to start our introduction to organic chemistry. So organic is usually a term used to refer to like living things, or organic matter would be living matter. Well, it turns out most living things here on Earth are made of carbon-based materials. We are a carbon-based life form. So organic chemistry in the chemical definition actually is just the study of anything carbon-based. So when we start looking at carbon-based compounds, we're going to have some unique names, and that's going to be the focus of Unit 14. First, let's look at a couple of categories for organic compounds. We could have saturated compounds or unsaturated compounds. And here's a picture of each. So what seems to be different between saturated and unsaturated fats, for example? The saturated would be completely surrounded with hydrogens, where you can see with the unsaturated, I am missing some hydrogen. So what is it saturated with? Hydrogens. Why is it saturated with hydrogens? Why is it missing some when it's unsaturated? Well, that would have to be caused by some double or triple or a combination of both, some kind of bonding that's going to make it so the hydrogens aren't needed to complete the octet. So now's probably a good time to mention that organic chemistry is an advanced chemistry, and it's expected that you already have a decent understanding of the octet. And you'll see that's going to allow us to save a lot of time later when we draw out the molecules. We should know that because of the double bond, I have 2, 4, 6, 8 electrons already. I would not have the extra hydrogens here. So the double and triple bonding causes the lack of hydrogens, but then it's that lack of hydrogens that is what we're calling unsaturated. And these are your healthier fats as they can bend through your body, I guess. And then the saturated fats are solids more at room temperature, and these are going to be your more unhealthy fats as they're more rigid. So in a chemical definition, saturated compounds are full of hydrogens because they have to have single bonds, where unsaturated hydrocarbons would have a double or triple bond, meaning they have less hydrogen, not saturated with hydrogens. So we actually have 3 different categories for all the different naming things, and it's all bond-based. So saturated hydrocarbons are alkanes by definition, and that means they're going to have all single bond, which is what allows them to become saturated. But then you have 2 different types of unsaturated alkenes and alkynes, 2 different types of unsaturated hydrocarbons, I should say. If they're double bond based, then we would call them alkenes, and if there's triple bonds, we would call them alkynes. And either version here would result in an unsaturated compound because that bonding would mean that we don't need as many hydrogens, leaving it unsaturated with hydrogens. So we've got kind of a lot of different categories going on here that's going to help us figure out what's going on with the hydrocarbons. When we name the hydrocarbons, we are going to use a prefix and a suffix. And don't tell your English teacher, but there's nothing in between. We're going to take a prefix and a suffix and put it together and call it a word. So first, let's talk about the prefixes, the beginning half of the name. It's going to be based out of how many carbons there are in the ring. So the first 4 are fairly unique to organic chemistry. If there's only 1 carbon, we would say meth. If there's 2, eth, 3, prop, or 4, bute, like butane would have 4 carbons. But then the rest are very similar to our molecular prefixes or geometry prefixes, even continuing patterns like dodeca for 12. But we do have 4 new ones that we want to make sure that we know for our organic chemistry naming: meth, eth, prop, and bute. Now we're going to combine these with suffixes, and the suffix is going to be based on whether it was an alkane, an alkene, or an alkyne. So we just take the ending of that name, A-N-E, E-N-E, or Y-N-E, and make that the end of the organic molecule. So for example, butane would have 4 carbons with single bonds, butene would have a double bond, butyne would have a triple bond, but the bute on all of them would mean all of the molecules have 5 carbons. So let's start looking at some of our alkanes and see how the name connects to the structure. So this is our first one, methane. So meth would mean 1 carbon, and A&E would be single bonds. Of course, that's all we could have for meth, since that would be 1 carbon attached to hydrogens. There couldn't be any kind of methene or methine, that doesn't exist. So it's just methane. When we look at 2 carbons, we can see we use eth for the 2 carbons, and then the ANE would indicate a single bond here. Or we could say ethene if there was a double bond here, or ethine if there was a triple bond here. So we're using the prefix to determine the number of carbons and the suffix to determine the bonding. Let's stick just with alkanes for a few minutes. If I had propane, I would now have 3 carbons attached to each other by single bonds because of the ANE. I mentioned that you're supposed to already know about the octet rule. Here's where it's really going to come in handy. Why would we bother writing H all the time if we are supposed to know that there already is H's surrounding it based on the bonding? So if you change the bonding, then you would be changing the H's, which we can just represent the attachments here, the bonds, with these dashes, instead of having to write the H over and over and over again. There's actually an even more, I don't know what to call it, more complex version. We call them stick figures. So every point would be a carbon. So 1 carbon, 2 carbon, 3 carbon. I could just draw propane like that. But we'll save that for college. Kind of a funky little version of drawing organic molecules. Carbon, 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 and then we just assume it's saturated with hydrogens because it's an alkane. If we had butane, we would just change this to show 4 carbons, assuming everything is surrounded with hydrogens because it's an alkane. Pentane, same thing. Picking up the pattern here, hexane, 6 carbons surrounded by hydrogen. So however many carbons we're drawing, the assumption is that as long as it's an alkane with all single bonds, every carbon around it would be surrounded with hydrogens, and we're just going to show the bonds with little dashes. All right, let's look at a different version of a molecule other than an alkane and see if we can kind of determine some other patterns. Let's look at how adding a double bond in would affect the name. The first thing you should be able to determine about the name is that because I have 1, 2, 3, 4, 5 carbons, the name is going to have the prefix pent in it. But it is going to change a little bit because of that double bond. First of all, the hydrogens that are attached are different. We have less hydrogen on the first and second carbon because I have the double bond there. So it would be assumed that the hydrogens fill in based on the octet rule. Then we change the ANE to ENE to acknowledge the double bond. And then finally, we have to say where that double bond is placed because it could be anywhere throughout the molecule. So it's between the first and second carbon, so we're going to call it 1-pentene. There's a rule we'll talk about later where you're always going with the lowest numbers. So we'll name it, or number it, I should say, 1, meaning it's between 1 and 2. So that's an example of how the name can change kind of based on the type of bonding that you see. Now let's look at a few more examples. We can actually have hydrocarbons that are not only in a straight chain like all the ones that we've looked at, but they can also branch off. So if they're in a straight chain, we call them normal hydrocarbons. And you can actually put an N in front of the name to kind of emphasize that this would be just that normal straight chain. Or we could have branches, and then we're going to have to be able to name and number the branches. These are going to produce different structures. So let's look at normal butane. N for normal butane. So BUT tells me I'm going to have 4 carbons. And then ANE tells me it's all single bonds, which tells me that I am going to saturate this molecule with hydrogens, meaning fill it completely up with hydrogens. The N tells me it's going to stay in a straight chain, and so I am done. That is normal butane, the same butane that we drew earlier. But what if we introduce some branching? Well, first we need to go over the rules for how to number and name our branches. So the first thing that you have to do when you have a branched molecule is find your base molecule. And that may not be what looks like the straight chain. It's always what's longest. So getting the most the most carbons in a row is the most important. That's going to be our base molecule. Then we want to number that base molecule, kind of like how we numbered the 1-pentene. And when we do that, we want to go with the lowest numbers possible, meaning we want to get to the branch the quickest, give the branch the lowest numbers. You're going to keep that numbering consistent. For example, you couldn't number 2 different branches 2 if they were on 2 different carbons, just because they were each 1 in. You would need to make sure you find the numbering system that works best for the molecule as a whole. So that's what it means by number all the way to the tail, meaning pick one numbering system. Next, we're going to go over a lot of different functional groups. And so we're going to figure out how to name each type of branch. And then if there's a conflict in numbering, the winner always goes to the first alphabetical. So we're going to go in alphabetical order whenever we have a tie. So those are our rules. Let's try applying them. So first, let's look at the base molecule, propane. The prop tells me I'm going to have 3 carbons. The ANE tells me it is all single bonded, but before I saturated, I want to look at what's my attachment, what's my branch. So in this branch, they use the prefix meth, which remember just meant 1 carbon. They use the prefix YL to indicate some kind of branch, and then the number tells me where. So I've got my longest chain here, the chain of 3, my base molecule, and I would number these, actually let me use a different color for that. The first carbon, the second carbon, and the third carbon. So the branch that I want to include, I want to put on the second carbon. And what the branch is a 1 carbon branch, meaning just like that. So let me get my numbering erased here. And then the last thing that I want to do is now to make it saturated. And that includes putting hydrogens on organic branches, like this methyl. We're going to have hydrogens surrounding this carbon just the same as we had the carbons, or hydrogens surrounding the carbons in the main chain. So that's how we are using the naming pieces to draw our molecule. All right. Let's look at normal pentane. So pent tells me that I'm going to have 5 carbons. The ANE tells me it's all single bonds. Before I saturate it, I'm going to look at my prefix here. The N means it's a straight chain, and I don't have any branches listed. So now I want to just saturate it. So this would be our normal pentane, one of the pentane molecules like we drew earlier, or one of the alkane molecules when we started. There we go. So let's look at a slightly different version, now a branched one, and I want to try to work backwards this time. So we've done a lot of name to drawing. Now I want to try one drawing to name. So the first thing that you want to do is find your longest chain. So this chain is usually everybody's first impulse, and that would have 4 carbons. But you do need to check, what if I numbered it this way? Well, that would also have 4 carbons. What if I connected this? Well, that would only be 3 carbons. That's not as good. So we want to kind of test out all of our different roads and try to pick the one that has the most carbons. So as it turns out, going straight across or considering this, the main chain, will have the same end result, same name. So we have 4 carbons. We know we're going to have bute in the name. The next thing you want to figure out is the type of bonding. So I don't see any evidence of double or triple bonding here, so I know it's an alkane. So I'll use ANE. The next thing I want to do is number the carbons, and I want to get this branch here, my lowest number. So would it be better to go 1, 2, 3, 4, or from the backside, 1, 2, 3, 4? Going forwards actually does make sense this time. 1, 2. So that would be my second carbon. And then now I want to name the branch, since it only has 1 carbon as the branch, not including the main chain carbon. This carbon is part of the butane. It's already numbered and labeled there. This is a separate carbon. So this is going to be meth. And then because it's a branch, I want to use YL. So this would be 2-methyl-butane. Notice how many carbons and how many hydrogens we ended up with here. C5H12. That's actually the same number of carbons and hydrogens that we had back with the normal pentane, C5H12. So there's a special name for that. When something has the exact same chemical formula, but has two different structures, two different names. We call them isomers. Structural isomers will vary structurally, but they would have the same formula. So anytime you have the same number of carbon and hydrogens, you're going to end up with different structures. You're going to have isomers. Not the same as isotopes, isomers. All right, let's look at one more version of a branch. Give this a little bit more practice here. First thing I always do is look at the base molecule and draw that first. So pentane, we have 5 carbons. And because of the A and E, I have all single bonds. But before I saturated, I have to determine what is going on in this branch. So let's start with something we do know. Meth, we know means 1 carbon, and the YL tells me that's the branch. So now the question is, what do we think di might mean? And you may know from prior experience, di typically means 2. Now there's these numbers up here, and these numbers typically tell me where. So why do we think there are 2 numbers telling me where? Well, probably because I have 2 1-carbon branches that I need to attach. As it turns out, every branch needs its own number. So if you see 2 numbers, you know you have 2 branches. If you see 3 numbers, you know you have 3 branches. So on my second carbon in, I'm going to attach 2 separate 1-carbon branches. Let me get this out of the way a little bit. 2 separate 1-carbon branches. Dimethyl is different than ethyl. This would be an ethyl branch. We don't want an ethyl branch. We want 2 methyl branches, or dimethyl. Once we have the branching figured out, now we can go and add all of our hydrogens. Don't forget to add them also to the branches. And actually, yes, you can use that weird little stick figure with stuff like this. Let me just show you this one for an example. I had 5 carbons in my chain, right? So 1, 2, 3, 4, 5. And then on my second carbon, I have 2 branches. 1, 2. So this would represent 1, 2, 3, 4, 5 carbons in the branch, and then the 2 separate methyl groups. And that would be interpreted as 2,2-dimethylpentane. All right. So I want to use their version here that they've got drawn to talk about numbering. This is numbered and labeled as 2,2-dimethyl. But if you were going from left to right, this would be 1, 2, 3, 4 carbon. So why is it actually named 2,2? Well, that goes back to the rule where you have to get the branches the lowest number. We have to consider numbering not only 1 through 5, but also 1 through 5. 1 being at the end, 2, 3, 4, and 5. So because going from the back gives this carbon the lowest number, that's what I'm going to name it. This is going to prevent us from naming 2 molecules that are actually the exact same thing 2 different ways. Because what I drew and what they drew are exactly the same. It's just flipped. And you don't start going by a different name when you flip on your head, right? So we want to make sure that we're not confusing the same molecule just flipped as an isomer or something like that. So we want to make sure we're following our rules and go with lowest numbers so it ends up with the same name. All right, let's talk about cycloalkanes, which is exactly what it sounds like. We're going to have alkanes in a circle, circular alkanes, cycloalkanes. So something like this, cyclopentane. Cyclo tells me I have a circular pattern. Pent tells me how many carbons, so those prefixes are going to be in everything. And then the ANE shows the single bonds. That little stick figure thing that I just showed you is used a lot more often with the circular things. It just seems to be more natural for people, I think. And you're fine to mix them up. Like, for example, if we had a branch off of here, we could go back to using the carbons and the dashes, but still use the stick figure shortcut to represent the 5 carbons in a circle. So either way works just fine because we understand the octet rule, right? All right, so what do we think cyclobutane would look like? So the cyclo tells me I'm going to draw in a circle. The bute tells me I'm going to have 4 carbons, and then the A and E is your single bonds. So I have in a circle 4 carbons with single bonds. So something like this. And then every carbon, because it's already got 2 bonds, would have 2 hydrogens attached. So it kind of looks like a hashtag or something there. Or we could just draw it as a square to represent the 4 carbons at each intersection. Carbon, 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 carbon. Okay. All right, let's try naming one big one, a cycloalkane in a circle, which has 2 separate attachments, so that we get a chance to practice that ABC order rule. So first, let's start with the main molecule, which if you have a cycloalkane is of course going to be that cycloalkane. I have 1, 2, 3, 4, 5 carbons in it, so I'm going to call it a cyclo to acknowledge the circle, pent, based on the 5 carbons, and then I don't see any double bonds here, so this would be A-N-E, cyclopentane. Now I want to name the branches. So they've got it kind of set up for us here. On top I have just 1 carbon, so the prefix is meth. And down here I have 2 carbons, so the prefix is F. And then notice because I've got branches, we have YL. So basically we have the methyl group versus the ethyl group. So now I need to figure out which way to number it. I definitely want these to have the lowest possible numbers. So I'm definitely going to be going either 1, 2, 3 or 1, 2, 3. I would never go 1, 2, 3, 4. That number 4 is higher than any of my other options, bouncing back and forth between the 1, 2, 3. So that's why I'm limited here. But I need to figure out now, is it the red numbering system or the green numbering system based on ABC order? So E comes before M in the alphabet. So E is going to come first in the numbering system, meaning it's going to win and get that number 1 spot. So then I would go with the red numbering system overall, not the green numbering system at all. You can't mix and match. So this would be 1 for our ethyl and 3 for our methyl. So now we're just going to write all that in the front here. 1 ethyl, 3 methyl, cyclopentane. Still got that same base molecule. We just figured out our branches. Oh, sorry. There we go. 1 ethyl, 3 methyl, cyclopentane. All right, let's move into alkenes, things which have double bonds. So whenever you have a double bond, you change the ending of the name to the ENE. This is what's going to show me that I have a double bond. And we always have to indicate where to put that double bond. So that's why you have the 2 in front. So pent, again, is a starting place. So I have 5 carbons. And then the ENE tells me I have a double bond. I'm going to look at the number to figure out where. It's always the lowest of the 2. So if I see a 2 here, that tells me the double bond goes between 2 and 3. If you saw a 7, you would need to know the double bond goes between 7 and 8. It's always between this and the next one up. So if this is my first carbon, second carbon, third carbon, it's between the 2. Now here's where you have to be careful about adding your dashes. Wherever the double bond is, we'll have less hydrogens. Here I only have 1 bond, so I need 3 hydrogens. But on my second carbon, I already have 6 electrons in these 3 bonds, so I only need 1 more hydrogen. Same on the next carbon, and then I'm back to just filling everything. So this is what leads to those unsaturated compounds because we have the double bond. So now we don't have it full of hydrogens. All right. Let's do another one. So 2,4-hexadiene. So let's start with what we know. Hexa will tell me how many carbons, and that means I'm going to have 6 carbons. 1, 2, 3, 4, 5, 6. Now I can see that ENE that I'm used to, but there's a di in front of it. Well, think back to dimethyl. What does di usually mean? 2. And what does the ENE usually mean? The double bond. So diene would just mean 2 double bonds. Notice how I have 2 numbers, 2 locations to tell me where to put each of the 2 double bonds. So the 2 means I'll have a carbon or a double bond between carbons 2 and 3. And a 4 means between 4 and 5. So then when we add the hydrogens, we have to be really careful. This needs to be full, but here I already have 6 bonds, so I only need, 6 electrons, 3 bonds, so I only need 1 more. Same here, and then same here, and then at the end I'm back to needing 3. So we have a very unsaturated compound where we have only 1 hydrogen needed on the carbons that are in between. All right. So double bond, single bond, double bond, by the way, is called being conjugated. So this would be a conjugated double bond, important kind of bond. All right, let's do alkynes, now using the ending YNE. So butene would have but, so 4 carbons, but it's going to have a triple bond. But just like with everything else we've done, this function is described, the location is described by the number in front. So I've got my first carbon. So between carbon 1 and 2, I would have a triple bond, meaning I only need 1 hydrogen on the first carbon. I don't need any more hydrogens on the second carbon, and then I can complete the end like normal. So you really got to watch your hydrogens with these double and triple bonds. This would be our 1-butene. All right, so now we have a pentyne with a branch. So pent means I'm going to have 5 carbons. The YNE means I'll have a triple bond. Here I can see where, between my first and second carbon. And then this will be my branch, since I have the YL. That branch is supposed to have 2 carbons in it and be located on the third carbon. So if this was 1 and 2, same numbering system, this will be 3. And off of it, I'm going to put a chain, an ethyl chain. Not 2 separate methyl chains, but an actual ethyl chain. So it's this repetitive pattern of using the prefix to figure out how many carbons, and then breaking down the functional groups, using the numbers to figure out where to put the attachments. So that is our ethyne. I'm sorry, not our ethyne, our pentyne with the ethyl group. Now let's talk about a very special type of hydrocarbon called benzene. This is going to be a host or starting point for a whole family of derivatives, things that are derived from or made from benzene. So let's talk about what benzene is to start with. Benzene is a ring of 6 carbons, which has conjugated double bonds, meaning every other bond is a double bond. Double, single, double, single, double, single. Well, that will automatically have resonance, right? Where those double bonds could be in either set of places. And so the true structure would be an average of bouncing back and forth between these 2 drawings here. Notice that because we have double and single, we only need 1 more hydrogen on each one, also, by the way. So the formula here is actually C6H6, our benzene. But we don't want to have to draw this every single time. We're trying to draw all these other attachments. So there is a simpler way to draw benzene. And that's just by drawing the 6 carbons in the little stick figure form, and then putting a circle in the middle of it to show that there is resonance. There is a rotation of the double bond. So If you just drew the stick figure, that would just be cyclohexane. But the second you put the circle in the middle of it, it becomes benzene. And you usually don't draw the circle so big. You usually draw it more like that. Okay, so that's benzene, what it is. Now let's name some things that are attached to it. So when you go to the starting point, our normal starting point was to draw the base molecule. I see benzene. So that means that I'm going to draw that six-sided figure and remember to put my circle in the middle. Now I've drawn benzene. I have a habit of making the first carbon the very top of the benzene as I draw it, so that's probably what you'll see in a lot of my work. But it really doesn't matter because the benzene would be able to rotate and you would use the rules of numbering and give them the lowest number. So pick where you want to start. What's important is that they're connected correctly. So 1, 2 would indicate that I'm right next to each other. 1 carbon, 2 carbon. It would be the same molecule if I made this 1 carbon, 2 carbon. Now let's talk about what the attachments are. F meant 2 carbons and meth meant 1 carbon. So I'm going to have one attachment with a couple of carbons and one attachment with only 1 carbon. And that does not include the 6 carbons that are already here. So let's put our 2 carbon attachment on the first one. 1, 2. And then put our 1 carbon attachment on the second one. Now the attachments need hydrogen, so we're going to draw our H's. So this would be how we would draw benzene with the methyl and ethyl group attached right next to each other. Now this molecule could be flipped, could be rotated. So all of these things would be correct as long as your methyl and ethyl groups are right next to each other. You'd be drawing the same molecule, not an isomer. See, so they have it drawn, shifted down. They made this their 1 carbon, this the 2 carbon. They're still right next to each other. We have our methyl. Actually, they made this their 1 carbon, ethyl group, and then the methyl group. So 1, 2. All right, let's look at quite a few attachments on my single benzene molecule. So here I have the benzene as my base molecule. Remember to put the circle in the middle. Now I'm going to have methyl attachments and propyl attachments. So meth, remember, just means 1 carbon. Prop, we haven't seen in a while, means 3 carbons. These are our attachments, and I can tell because of the YL. So in front, we have numbering 1 and 2 to show where 2 1-carbon branches would be. And then we have a number 4 to show where my 3-carbon branch should be. So I'm going to stick with 1 being at the top here and put one of my 1-carbon branches on. Then I'll go over to the 2nd carbon and also put a 1-carbon branch. These are my 2 separate 1-carbon branches. Then I want to go all the way to the 4th carbon. So if I made this carbon 1, carbon 2, carbon 3 doesn't have anything. You go all the way down to carbon 4, and then you're going to attach 3 carbons in a row. 1, 2, 3. All your branches need hydrogens, but the hydrogens on the benzene are assumed. So this would be your final product for your 1,2-dimethyl 4-propyl benzene. Any variation of this where it's just shifted or flipped would be fine too. You just got to get your spacing right. Follow those numbering rules. So here they have 1, 2, 3, 4, drawn the same thing. The 3-carbon attachment, my propyl group on the 4th carbon, and right next to each other, 2 separate methyl groups, all on benzene as the base molecule. All right, that's going to do it for Introduction to Organic Chemistry. In Unit 14 Notes B, we're going to look at some other special functional groups because we can attach a lot of different things other than just carbon chains to the main chain. So we're going to look at those functional groups in Notes B. We'll see you there.